Good day. It is Friday morning on the 14th of the 7th. Let's talk about what's been happening. Sometime between my last video, which I think was about 3 days ago, and today, I came across this this conference, Cognitive AI 2023. The due date for their papers was yesterday. And so I worked my tushy off and I submitted a paper. That paper is in the shared OSF repository if you're interested. In this video, I'm going to talk about that paper, some of the interesting findings and some of the issues with the model that I had to run. So I used the existing Glasgow norms model, but obviously I didn't have the NRC models constructed. Bear with me a second. I didn't have the NRC models constructed, so I had to very quickly do those. We're going to talk about the code for those models, and then we'll talk about the results of that analysis. This is the code for the NRC models. It is very similar to the code for the Glasgow norms, with a couple of exceptions. There's no median split because the NRC dependent variables are already binary. If you recall, there's about 90% of those are null values, and about 10% of those are the actual, have a value of 1. The reason for that is because it was a completely different experiment to the one that elicited responses from the Glasgow norms participants. What this is like if you're given a word and then you're asked, does this word elicit a certain emotion? What kind of, like, this specific emotion? And then you give us and then it's either a yes or a no, right? So like words, not every word elicits a certain type of emotion. Yes. So the point is that there are 90% null values, which is really problematic, as I showed in an earlier video with the XGBoost algorithm, because it learns if there is a distribution skew, it knows that, and it adjusts its predictions based on that information. So you need to make sure that you've got balanced sample groups. Same as usual, parallel processing. Here is the tuned hyperparameters. All right, now here's where we start to get a bit different. We start building our k-folds, then recombining for testing samples, recombining for training samples. And now here's where the balancing occurs to balance those sample groups. I've done this after the k-folds. The reason for this is that because we're dealing with 90% null values, you're going to lose 80% of your samples that won't be included in the k-folds, because you need to balance them. So you've got 10% value of 1, 90% value of 0. You need to balance them so that 90% becomes 10%. You end up with 20% only of the original data set. That number is less than 10% for a number of the emotions. But yeah, just as a rule of thumb, we'll call it 10% for the moment. So why are we sampling that after the k-folds? If you did it before the k-folds, then you would be discarding 80% of the samples that would have no chance to contribute to the model. However, by doing it after you've constructed the k-folds, which is it's a much more intensive thing to code. It took a lot longer for me to code because I had to code for every single k-fold. But doing it after the fact means that every sample has a chance of being involved in every model. Whereas if you do it before the fact, then you're automatically discarding 80% of the samples, which will never contribute to any model. So it allows for more randomness. It means that you're not just discarding forever one particular thing, and then that would mean that the algorithms never get a chance to train on that sample. right? So this is a way of making sure that every sample has at least a chance of being involved in the training process and the testing process. Because this does both, right? This is, so fold number 1 for the anger, this is the training subset, this is the testing subset. So it's done for both subsets. You don't, I could have just done it for the training subset, but then during the testing process, we probably wouldn't have enough sample. Like it would, yeah, it would be trying to balance to a 50-50 split. But you would have a 90-10 split in reality. So it would play with your accuracies, and have a detrimental effect on them and your analysis. So no, thank you. Long story short, then this is the construction of the models. I did tune these models. Pretty sure. Let me just check. No, I didn't tune these models. Okay. Yes. So the tuning process is a very time-intensive process. The data, like the samples are almost identical. The samples are almost identical because they're all essentially a phoneme count. A phoneme count. Oh, that's interesting. Let me just check something, because I think I might have just realized what an outstanding. Oh, no. Nope. These are okay. Cool. So the NRC data, the NRC models don't behave the same way as the Glasgow norm models. And I was thinking it's probably one of two things. Either I've made a mistake somewhere, which is entirely possible, or because these are trained on fewer samples, that would explain the lower accuracy, and that's what occurs to be happening here. Because I haven't made that mistake that I was afraid that I might have made, which would have been forgetting to divide the number of phonemes by the length of the word, which is something that we do to try and limit the influence of word length. So safe, no problem. All right, so obviously this is the anger model. This outputs the file the same way we did with the Glasgow norms, and then it outputs the feature importance scores. All right, inside the shared OSF file, you will find this paper, which documents the outcomes of these models. Now, this is a conference proceedings. It is not the final, it's not presenting the final models. And obviously, if you've been watching all of these videos, you know that we're not finished with this project. We still have to figure out directionality. There's some things that I want to do with the NRC models, which I didn't have time to do before I submitted this paper. But that's the nature of conferences, right? Like you give them what you have at the time, they will, and then you can, you kind of adjust once you go and present. You can go and present the full model at the conference while you're submitting the full paper to an actual journal, as opposed to a conference proceeding. Let's take a look at these tables. This was a lot of fun to write. This was 3 pages. So I had to be really conservative as to where I spent my words. And obviously my introduction section has taken a bit of a hit. I think it's 3 sentences or maybe 4 sentences, but it is, yeah. It's not, I would not call this a literature review. This is, yeah, just a very basic introduction, because really most of what I've had to do here is talk about the method, which is really important, and also explain the results, which I've done essentially in tables. So this is the results section for the Glasgow norms. There are 2 sentences and a table, and that's it. That's all I had space for, unfortunately. If we zoom in on this table, because obviously I had to make this table incredibly small to get everything on the page, you can take a look at we've got the IPA of the features, the importance score of the features, but obviously there's no directionality here. And once I figure out whether I'm going to be using Shapely or my own homebrew method for determining directionality, then I'll add that into the final paper. But at the moment, that's not included. All I'm doing here is reporting which sounds are important, which phonemes, sorry, are important. So yes, pretty straightforward. You've probably seen this data before because this is the Glasgow norm stuff. We come down to the NRC one, and I've made a bit of a mistake. This should say NRC, but my cutting and pasting has bitten me in the backside. Anyway, here are the models. We note that they are less accurate than the Glasgow norm models. Everything is significant. So there's two methods that I use for combined significance values. Those are Stouffer's and Fisher's methods. When I ran those equations against my my p-values, the Fisher's method was the more conservative, so it gave the highest p-value, and those are the p-values that I report in the paper. However, everything is less than 0.001, except in the case of surprise, which, pardon the pun, is kind of surprising. So surprise had the lowest accuracy of all of the models, and it it was significant, but it was something like 0.02 something, 0.022 using Fisher's method, and 0.021 using Stouffer's method, right? So it was significant, but an accuracy of 51%. Now, I was thinking maybe surprise would be something that was pretty robustly reflected sound symbolically in American English, because when we are surprised by something, we go, "Wow!" Right? We have this kind of, there is this automatic verbal response to surprisal. However, that might be the reason why surprisal isn't reflected sound symbolically in American English. It might be because we already have this involuntary response. Anyway, that's kind of an interesting thing and something that I will probably have a lot of fun discussing with my co-authors when we get to that stage. Anyway, let's get to the general conclusion, the kind of stuff that I've been teasing for a while, but I haven't talked to you about yet. So in my opinion, so in this study, we're looking at these 19 sentiments and emotions. And one of the things that I was testing is sound symbolism in American English, is it so fine-grained that there are specific sounds that relate to specific emotions? And that does not seem to be the case. That does not seem to be the case, with caveats. So but these models are accurate, right? So what's happening? Well, it seems like the same sounds are reflective of different emotions, even when those emotions are opposed to each other. So if we take a look at the positive and the negative in the NRC data set, we see a very, very similar distribution for the feature importance of these models, right? Even though they are reporting the same thing, we do have there is a like more voiced plosives here, right? And voiced plosives are normally associated with larger entities. Larger entities. We did a go and find my Pokemon study on the base friendship metric. It's in that one we looked at voice plosives, and voice plosives indicated like a low base friendship. So less friendly Pokemon have more have more D's and G's in their names than more friendly Pokemon. Anyway, these models are very similar. So what's happening? Well, much like we talked about how length So the valence for length, we have a very weak positive correlation that is significant. And then we have the negative and positive sentiments. We have strong positive correlations for both. The valence but that's stronger in the positive emotion, right? Now, the valence is a two-tiered test, which means that a low score is negative, a high score is positive, and a mid score is default, whereas these are one-tiered tests, which means that a 0 is default, and a 1 is negative or positive, depending on which metric. Now, the reason why this still shows a positive correlation is because positivity is more robustly reflected in length than negativity, okay? But length still reflects both of these sentiments. Well, the same thing I think is happening here. We get the same sounds reflecting these emotions. So it's not that sound symbolism seems to be reflective of specific emotions. It's that sound symbolism seems to be reflective of any emotion, right? There is an unemotional state and an emotional state. And regardless as to what that emotion is, that's what seems to be reflected in sound symbolism, which is kind of interesting, but there are caveats here. The number one caveat is that phoneme frequency seems to be really, really important, seems to be contributing to the feature importance, particularly in the NRC models. If you recall, the low mid back vowel is the most common sound in the data sets. And here it is 9 out of 10, the most important phone. You see that's a little bit less prevalent in these data sets, but remember these are built on a larger number of samples because it's a median split rather than like the balancing is done on the median split rather than the balancing being done on a 90-10 split. So we lose maybe less than 1% of our samples in the balancing for the Glasgow norms, but we lose 80% of our samples in the balancing for the NRC. The NRC starts with more samples, it's 14,000, whereas the Glasgow norms is 5,500, but 20% of 14,000 is less than 99% of 5,500. So long story short, geez, that was a long-winded way of saying there are more samples in the Glasgow norm model, and that might be contributing to this. So that vowel, however, it's still showing up. Like I think it's in every single model, right? So yeah, it's just something to be aware of, and that might, like that effect for that low back vowel, that might be what's driving my hypothesis, right? Because all of the sounds that are important in these models, they seem to be very closely aligned to each other. And they're all high frequency sounds, right? So this is kind of problematic. However, what's interesting is that not all of these are correlated, have a relationship with word length, right? And not all of these have a relationship with word length. If you recall, there is no relationship of gender, the gender Likert scales with word length. So this can't be being driven entirely by sound frequency. I don't think. Maybe it can. Haven't really thought about it well enough, but just something to think about. All right. What else? Most of the consistently important consonants are produced at the alveolar ridge. Seems kind of interesting. Here is where I talk about the issue of phoneme frequency and how that is probably contributing to the feature importance scores. This file will be in the OSF file that is linked below. So yeah, if you're interested in reading it, it's only 3 pages long. Go and take a read. All right. That's enough for today. I will catch you in the near future. See you later.